Thank you very much for this nice introduction. Yes, indeed, I'm an engineer, electrical and computer engineering. So my talk is going to be a little bit more technical, and I will try to be brief and, you know, as understandable as possible. So this is, I'm sharing my, you know, slides here. I'm going to use them during my talk. All right, so as I said before, I'm an engineer, and my talk is going to give some technical, you know, details about the blockchain. So the title of my talk is Re-engineering the Internet for Security, Privacy, and Trust with Blockchain. So it's a very, very, you know, interesting, you know, topic, and I'm just going to talk about this. Okay, so this is the outline of my talk. And I will start with the online transaction. So whatever we do in the internet, you know, we call it an transaction, right? So these are being done on online world, and this is an online transaction. First of all, I'm just going to basically talk about the idea of the online transaction. And then I will talk about the security, privacy, and trust and transparency of it, because these are the features, these are the properties that we want to provide to online transactions. So because online transactions is not trustable without all these properties. And then I will talk about the blockchain technology, giving some theoretical foundation, what makes the blockchain technology so fascinating, so powerful, and also feasible and possible in our, you know, everyday world. All right, I'm just going to talk about the consensus protocols, some cryptographic background, and etc. And then I will mention about our, you know, current project, which is about trust and identity management in the internet. And because, you know, all these things do not exist, you know, originally in the internet, because internet was designed for functionality, basically sending messages from one point to another point as efficiently as possible. But they didn't think too much about the trust, identity management, security, privacy, and also for transparency. And this probably at this point basically brings us about to the re-engineering the internet part. All right. So I will continue. All right. So well, let's take a look at the transaction. Anything we do, you know, between two or more parties on the online world is we call transaction. All right. So there are two types of, you know, transaction. One is unconditional, the one that happens in the blockchain network, like Alice sends certain amount of money to the Bitcoin to Bob. Okay, and Alice does it, you know, no matter what, because there is no condition, you know, based on this transaction, right? Alice decides to send a transaction to Bob, and everybody in the network basically is aware of this transaction, and this transaction are being seen and validated by the network. Okay, but of course the more difficult, you know, transaction is a conditional transaction. You know, the activities in a transaction depend on a certain conditions. All right, we model this conditional transaction as a coin tossing experiment, right? So just a simple type of, you know, a little bit, you know, a sophisticated transaction, all right? Someone, you know, toss a coin, flip a coin, depending on the outcome of the coin tossing, either Alice sends money to Bob or the other way around, okay? So this is a conditional transaction, all right? So the first part, you know, is being done in the Bitcoin, the conditional transaction, but the conditional transaction require something, you know, smart, which is called smart, let me say, smart contract. Okay, so, and of course the idea about in the blockchain that, you know, all these conditional transactions are seen and executed by the participant of the blockchain. All right, I'm just going to give too much data. This is just the model, just to illustrate, you know, what is happening in the blockchain, what kind of problem that we are solving in the blockchain. All right. So it is like, you know, flipping a coin. I said it's very important for our transaction because a conditioned transaction in the physical world, this is what happens, right? You know, there is a referee and it is flipping a coin, you know, to decide which team is going to, you know, kick the first ball, all right, in a football game, for example. And even, you know, two parties see the outcome of the result, they still don't trust each other, right? This is why they need a trusted third party referee, right? So you need that one. All right. But of course, on the online world, coin tossing is extremely difficult because those parties do not see each other and they need a trusted third party. And it may be difficult to find a trusted third party whom both parties trust. Okay. So what are you going to do about it? Because it's an extremely difficult thing to do on the online world. All right. So, and then this means that we don't like this trusted third party. And what is the ingenious, creative solution to when you get rid of the, trusted third-party referee? So what is the solution that is being offered in the blockchain? In fact, put everybody together, right? So now, all these members of the, the blockchain network, they are going to basically form a network. And this is the way they are going to make a consensus on the result of a certain transaction and everything. And that is how we, create trust using blockchain. It's like crazy idea, but it works. All right. So that is the idea. We don't have a trusted third party because the whole blockchain network, all the participants, all the peers are the trusted third party. All right. So since we don't have a trusted third party, we don't have a single point of failure, and there we don't have a single point of attack, and we don't basically put all the eggs in the same basket, because if we are talking about the data, every peer, every node in the blockchain has the same thing. All right. So no matter where you go, you can go and get the data from him. And if one node is down or one certain number of nodes are corrupted, they are not functioning correctly. So don't worry, because there will be always honest and up and running, peers in the network, so that you can, get things done or reach data. All right. Of course, we, with the blockchain, we provide security because, the transaction happens in the online world. We don't want those transactions to be interfered with some unauthorized parties, some parties with malicious intents. Okay. And we want, privacy in the network because we want to keep certain aspect of a transaction secret and private. For example, how much money you are transferring, who you are sending this money in the, or whom you are interacting with in the transaction. So we just want to keep those secrets. This is privacy. And also transparency, because usually what we want to do here is that we have to know that whether those transactions are valid or not. All right. And what we require is the public verification of the validity of all those transactions. Everybody should be able to, go ahead and check the validity of the transactions. That is important. This is transparency. All right. So this is an amazing technology. It's hard to believe that it works, but what makes this technology, blockchain technology works. And first of all, that brings us to, of course, the theoretical foundation part, right? And cryptography. In fact, I'm an applied cryptographer. I have been working in cryptography for the last 30 years. And cryptography, basically gives the tools that, the blockchain, make the blockchain possible. All right, most of the people think that encryption, when you just tell them cryptography, and encryption is for encrypting, your messages, your data for confidentiality. But because from blockchain, perspective, this is the most unimportant, functionality cryptography provides us, because, encryption confidentiality has been done for thousands of years. All right. So this is not really interesting for us. What is interesting from the blockchain perspective is the, cryptographic hash functions, simple functions. I'm just going to describe them in a moment. And this is the essence of the, blockchain. This is how you can basically, link one block of transaction in your chain to the another one. And this way, by forming this, the chain, you can basically establish an order among the transaction, which transaction comes after the other transaction, and also immutability of the transaction. Whenever once the transaction becomes a part of your blockchain network, you cannot change it. This is what's called immutability. This is why we trust the blockchain, right? There is an ordering between the transactions, whatever. When I say transaction, I'm not meaning only, sending money. It could be anything. And as the other, speakers of this webinar will point out, it could be anything, any transaction, or those transactions doesn't have to involve, the money transfer. It can be anything else, all right? So the electronic signatures, they are important because when you initiate the signature, transaction, you want to ensure its authenticity, integrity, and of course, you have to basically ensure that you cannot deny it later, right? This is what's called non-repudiation of the transaction. And this can be done only by electronic signatures, e-signatures provided by cryptography. And the last one is more exotic. It's called zero-knowledge proofs. And so this is being used, increasingly for the privacy of transactions. It's a very esoteric, very exotic, cryptographic protocol. And I'm just gonna, give you very important. It's gaining more and more importance because we care more and more about the privacy of our transactions on the blockchain network. So don't worry, I'm not just going to say too many things, too much technical details about cryptographic hash functions. I'm going to say a couple of things. You have to keep this in mind because you really have to understand, what blockchain offers. Okay, hash function is at the center point of the blockchain. One-way hash functions, they are one-way, meaning that you just take one message, apply this function on the message, it just creates you fixed length output, which is ones and zeros, right? This is a digital world, all right? This is because of hash or hash code, okay? So here, this is one way, meaning that given a message, you can very fastly compute its hash, but given the message hash, it is difficult to invert it and get back to the message. So this is one way property, which is very important. Just keep this in mind. And there is another property of hash functions, which is called collusion resistant, meaning that, okay, so as I said before, the message could be anything. And there may be infinitely many messages, okay? You just take them and digest them, compress them, maybe you can call it, and you just get a fixed length, which is 256-bit long, for example, right? And apparently there will be a lot of messages that is giving the same hash value, apparently, obviously, because the set of messages is big, set of hash values are small, so there may be a lot of collusion. But the point here is that in cryptographic hash functions, it is computationally infeasible or impossible for you to find two messages giving the same hash value. So this is two important properties of the cryptographic hash function. And by the way, cryptographic hash function is not about security, about encryption. It doesn't require a secret key. It is not an encryption. It's a public function, meaning that given a message, anybody can compute its hash value, but not the other way around. All right. So these are hash functions, and I'm just going to basically explain how we make use of them. Digital signatures, again, is a cryptographic algorithm. Given a message, a signer holding a private key, sign the message, and there will be a signature. And this signature is not only tied to the signer, but the message being signed. So therefore, when you just see a signature, you can just basically identify who signed what. And later on, for example, nobody else can, for example, change the content of the transaction once it is being signed. Okay, so that is the idea about the digital signatures. And digital signatures are possible because there is something called public key cryptography. It's an encryption type of function, but it's a little bit different. And in the public key cryptography, we have two types of keys. One, everybody has it. One is the private key, which is something secret, and you have to keep it secret. You have to keep them in your digital wallets or in some hardware devices, because it is extremely important that you do not compromise, those keys, because this is the private keys are the keys that you are using personalize or signing documents. If somebody steals it, he can or she can impersonate you. But the public key part, all right, is public. You just give everyone, you just announce, you just post it somewhere, everybody can get. All right. So because this is the idea. Do you do the signature, your private key? Since you are the only one who holds the private key, you are the only one who can sign a message on your behalf. But the public key is known by everyone. So this means that anybody can, verify your transaction if they know your public key, and your public key is public. Okay. So this means that your signatures are publicly verifiable. You just sign a transaction, you just broadcast your transaction to blockchain. Anybody can basically, verify your transactions are valid. All right, finally, the last one is what is called zero knowledge proofs. This is extremely, popular subjects nowadays. All right. So what is this about? It's a very complicated, very involved mathematical structure. But let me tell you what it does. All right. Let's assume that you have, in possession of a certain secret information. All right. And then you want to basically prove that to someone else that you know that secret information. Secret information can be your password, your secret key, or some other type of information like a digital signature entrusted to you. You just want to prove that you know that, you have that, without revealing a single bit of information of the actual secret. And the cryptographic machinery works there, and then you can just do that. Okay, so that is the idea about zero knowledge proofs. And people are crazy about those kind of zero knowledge proofs nowadays because it provides privacy. It helps you, for example, hide the content of a transaction. You don't want to, the amount in your transaction to be revealed sometimes. All right, the other things, these are cryptography part. And from computer science point, there are two things. All right, one is consensus. Remember, we don't have a single referee. We don't have a central authority who makes decision for us, like banks or credit card companies or government. What we have here is a network of people. They are peers, right? And whenever they verify some transaction, whenever they put a transaction in a blockchain, they do it using consensus. Right? They run a consensus algorithm, and then at the end, they make a decision. The network makes a decision. All right. And P2P is the peer-to-peer networks, and we achieve what is called decentralization here. We do not depend on a single point. All right. So here we don't have a server, we don't have clients here, we don't have a central authority, we don't have a certain central database. Here it is complete decentralized, meaning that all the nodes in the peer-to-peer networks are equal members of the network. So this means that they can act both, server and client at the same time, and all the data is distributed among the nodes of the, peer-to-peer networks. All right. So these are the two things which is important. So let me, basically, materialize or exemplify my discussion on the crypto coin transaction. All right. So, for example, we just want to send a certain coin to someone else. What do? We just basically sign the transaction content and public key of the next owner. Public key is in fact the hash of the public key of the next owner, because this is how you are identified in certain blockchain network, right? And by signing these two things, you just achieve this, right? For example, you cannot deny the transaction later on because you are the one who is signing this transaction. This is for non-repudiation. And legitimate payee, the receiver of the payment, and yourself are identified, right? This is authentication because you are signing it, willingly saying that you are, with your free, will, you are sending that amount of money to that, person. And also the amount in the transaction cannot be modified because you sign it. And if somebody changes it, it hasn't signed again on your behalf, but he cannot, right? This is the integrity. All right, so this is how the, transactions happens, especially coin transactions. But there's this problem here, double spending, because, whatever you call it here, the asset in the blockchain network are just digital information, ones and zeros, right? You know, it is very tempting to send the same thing twice, you know, to two or maybe more, to multiple persons. This is what is called double spend, right? You want to basically, you can make a copy of the coin easily, and you basically want to double spend it. All right. So because the recipient of the coin is not going to know whether this coin is sent to someone else or spent before or not. When we have a trusted central authority, well, this central authority has a big book called ledger, all right? And that central authority writes every transaction in that big book of this ledger, right? All transactions. So therefore, you can just basically catch a double spender easily, because if you just try to, you know, spend money twice, all the transactions are there. You are being caught easily. Or if you want to spend a Bitcoin that you don't own, it is going to be kept, you know, caught again, because you should have received that amount in an earlier transaction. And lives are easy. For example, you know, as far as a bank concerned, life is easy because there's a big book over there that records records all the transactions. But we don't have that, you know, central authority here. We don't, you know, have, you know, one big ledger recording or keeping track of all the transactions. Instead, we have a peer-to-peer network. So what do we do? This ledger is distributed, and ideally, all the net nodes are having the same, you know, a copy of the same ledger. So this means that anybody can, you know, can check the validity of the transaction, because everybody has the, you know, the copy of that book that records, keep track of the transaction. All right. So therefore, transactions are publicly announced. So this is why it is transparent, right? You just basically, you know, just broadcast, you know, all these transactions, and every peer in the network can record those transactions. But of course, in order to, you know, catch the double spenders and everything, or people who are trying to not spend the non-existent thing, you have to order those transactions. How are you going to do that, right? Because you have to basically order the transaction. One transaction comes before the other transaction, right? So this is important. If you have a, you know, timestamp server, you can do that easily, but this is not a, you know, a network with centralized authority. It is distributed and decentralized. And therefore, we are going to use those handshakes, all right? They establish the order between the transactions. So what do? We just put all the transactions that are publicly announced, every peer does it, in a block, and then you compute the hash of it. And then what do you do next? In the next block of transaction, you again compute the hash of the next block, but this time you are going to include the hash of the previous block. And you just keep doing that. And that is going to establish an order, time order between the transaction. As you see here, that transaction here, that transaction apparently coming before this transaction. Can you change the order? Yes, you can do so, only if you can invert the, let me see, okay. Invert the hash function. You have to go back in time. But what I just told you, it is not easy. It is computationally infeasible. Nobody can do that, you know, to invert the hash function. So this is why you cannot go back and change it, you know, a transaction in the past, all right? And that is bringing about what's the immutability of the blockchain network, all right? Well, of course, those blocks are in the Bitcoin network, consensus proof of work. Everybody knows about it. I mean, there are some details here, but I'm just gonna, you know, skip the details, say just this, okay? Well, it is not easy to compute the hash, because this hash, to compute this hash, you have to basically solve a cryptographic puzzle, and which takes some amount of time and some computation power, all right? In fact, if you look at a closer look at the blockchain network, those hashes are a little bit complicated, all right? So this is what is called proof of work. In order to include the hash, the block in the, you know, or just add, append one, you know, a block of transaction, you have to basically solve this cryptographic puzzle, then you can, you know, add it. All right, this is proof of work, okay? But of course, this is a peer-to-peer network. This is not ideal. So this means that at a given time, different nodes may have different chains. They will be consolidated later, but it can happen. But what needs to be done here is that the longest one must be chosen. All right. So let's see. There is, not all the peers are honest. Some of them can get malicious, right? To make gain advantage of this. What it can do is the following. Let's assume that there is a malicious peer and wants to change a transaction in the past, because maybe that peer made a payment. Let's see, for example, this transaction, and this peer, malicious peer, would like to delete this transaction from the past. Okay. Well, it can do so, but you know what he needs to do? He needs to recompute the hash of the block. All right. So this means that, but meanwhile, the honest peers keep computing hash of the new blocks. So this means that a malicious peer or the coalition of malicious peers should be able to compute the hash chain faster than the honest peers. Of course, if they have the majority in terms of computation power, malicious peers can, beat the honest peers. But what we believe is that majority is honest. So this is our perception, or this is our assumption in the case. Is this a good assumption? Can we just rely on majority of the peers are honest? Well, yeah, to a certain extent, because if you look at the current human societies, yes, most of the people are being and staying honest, right? Why? Because they have incentives, right? If they break a law, they can get fined or go to jail, right? This is enough incentive. And in the case of the blockchain networks, you have to basically award the peers to stay honest. All right. So for example, in the case of peers, since they are basically computing these next blocks and spending some computation power, either they ask for a transaction fee or just they can introduce a new coin in the network. So this is how they stay inside it. And so far so good. And and of course, in order to create a trust in a network, so you have to stay honest. And in the last couple of minutes, I'm just going to talk about our a project that we are working on. It is an application of blockchain. It has nothing to do with Bitcoins and everything. It's a completely different realm of application, and it is verifiable credentials. The most difficult problem in the internet is proving your identity, proving your credentials, who you are, what do you have, whether you have a diploma or certificate, driving license, or a title to your house, and etc. All these credentials, right? So it is extremely difficult, problem to solve, and there is no complete solution yet. And there is this cartoon from 1990s in the early days of internet, and there are two dogs talking to each other, and one dog is saying to him, the other said, on the internet, nobody knows you're a dog. This is about identity, right? And you don't know whom you are talking to. So, and what kind of person he is. Is it a bank? Is it someone else impersonating someone else? But furthermore, what you want to basically achieve here is that prove your credentials, your identity with selective revealing its content. Depending on the context, depending on the transaction that you are involved in an online world, you just don't want to reveal all information about yourself, okay? Maybe in certain occasions, you just want to say your name. But sometimes you just basically say you're a president of a certain company, a professor at university, etc. Right? That depends on and you don't want to really reveal everything. All right, so this is trust and identity management. So we just doing it, which is called, there is a blockchain, a particular blockchain technology called Hyperledger in the blockchain. Here we have people, and they need to keep their identity, prove their identity and credentials, and they have digital wallets. And there are issuers and endorsers. They have also digital wallets. So what happens here is that with the help of this blockchain network, the issuer or endorser basically give credential to people. It could be a diploma, a certificate, or something else, right? Of course, all these things are going to be done, using the blockchain network. what is interesting here is that issuer, in fact, digital sign the credential. And later on, for example, this person that has the credential in his wallet, when it wants to prove, his, credential to another person, he's not going to show the credential as it is, right? Because it is going to reveal all the information, because you want to reveal, reveal the certain fields from your credential, maybe just your name or a school that you are graduated from, etc. Right? You just selectively want to do that. And of course, in order to make the other guy, other person, other party be convinced about your credential, and you have to show that this is being signed by some issuer, like a university, Sabanci University, Politecnico di Milano, or something like that. Okay. But if you cannot show your credential as it is. You cannot show the digital signature, on your credential, because they are secret values. All right. Okay. You cannot do that. What are you going to do? You are going to make a claim. You are going to say that, okay, I'm a graduate alumni of Sabanci University from computer science department with a GPA over 3.0. Okay. So it's a claim. You are not saying anything. And then say, you're not revealing anything, just as much information as possible. Then the other person says, okay, you make this claim, but just please, prove your claim that you have that information. Okay, both the credential and the signature on the credentials are secret and private. What you are going to do? Of course, you are going to do what is called zero knowledge proofs. That is the only way you can do that. Zero knowledge proofs without telling the entire, credential and the signature on top of this, just prove that. And in the end, it works. Okay, so that is a project that we are working on. All right, my last slide. All right, re-engineering the internet, because this is the amazing title of my talk here. All right, so in the internet, as I said before, in the internet was designed for functionality, right? So meaning you have a data message and send that message from one point to another point as efficient as possible. That is the design goal of the internet in the very first place. Of course, there were other design goals, maybe, but they were less important. And trust, security, privacy, decentralization, or distribution are not the topmost priority. So this is why we are having all these problems nowadays. All right. And even, it is very difficult to prove your identity over the network. You need additional equipment and everything. All right. So that is the idea. And the blockchain technology could be the technology that solves this problem. And my last question, my last remark is this: whatever internet is in the 1990s, and blockchain is a candidate to be the same for 2020, for the next decade. And with this, I'm just going to conclude my talk, and I just thank you for your patience and listening to me. Thank you very much.